Thanks to the organizers for inviting me. Thanks to the sponsor. This is a great venue and it's a great city. It's time for Americans to explore other possibilities. It's also the time for deep nets, of course. And why is that? Well, the reason is that I believe that we need to understand intelligence, and that the problem intelligence is actually not only one of the great problems in science, like the problem of the origin of life or the origin of the universe or the structure of space and time, but it's probably the greatest one, because if we make progress on it, then we can more easily solve all other problems. And of course, we want not only to develop engineering and software and hacks, but also the science of it, because the engineering of tomorrow will come from the science of today. And so, in fact, if you look at what happened in the last few years, two of the great successes in AI and deep learning are AlphaGo, and this is Demis Hassabis here, and Mobileye, which was recently acquired by Intel. It developed autonomous driving systems. This is actually a deep network labeling the pixels in the image that are free for the car to drive on, and labeling with different colors at the borders the different type of objects from the curb in the street to other cars. It's interesting, this is a small parenthesis, this is real time, very good accuracy. This was 20 years ago in my lab, a project with Daimler. These are actually streets in Ulm, which is the site of the research lab of Daimler, and also, of course, where Einstein was born. And you can see that there was one of the very first systems based on machine learning, at the time support vector machines, trained on a few thousand images to detect pedestrians. And the point here is that there are a few mistakes. You can see the traffic light labeled as a pedestrian. At the time, we were very happy. This was 95. We had about 1 error every 3 frames, which translates into 10 errors per second, which means that, of course, it was not usable at all. And now, for the same problem, Mobileye is about 1 error every 30 or 40,000 kilometers of driving, which translates into 1 million times better accuracy, which is actually doubling every year for 20 years. So that's a kind of Moore law for deep learning. And the real point, coming back, is that in the algorithms and in AlphaGo and in Mobileye, there are two basic schemes. One is deep learning, the other one is reinforcement learning, and they are both inspired from neuroscience. For instance, deep learning, the architecture of it came from studies by Hubel and Wiesel in the 60s at Harvard, recording from the visual cortex of monkeys, and proposing a hierarchical structure for V1, the primary visual area, in terms of simple and complex cells. And there were quantitative models after that. This is one of them from my group, but the previous one by Fukushima, that showed how this hierarchical architecture could work. And the architecture, not the way of training, of course, but is the same in recent deep learning multi-layer networks. The most, probably the state of the art, more or less, is ResNet at the extreme right. So, skipping this, so the kind of ironic situation is that now these deep networks are used to understand better visual cortex. It's full circle back to the original inspiration. This is work by Danny Ammons and Jim DiCarlo, in which they show that units in the model have very similar tuning to to actual neurons in IT and V4 areas in the monkeys. And so this is really ironic because we are trying to understand something we don't understand, the brain, using models of something we don't understand, how they work, deep networks. So a theory is really needed. And let me try to tell you about some of the work we have done in this direction. First of all of you know, of course, that deep networks consist of multi-layers, simple weighted sum of inputs to each unit, a nonlinearity, which is these days can be more or less anything, but these days is the linear rectifier, and a training techniques that most of the time is stochastic gradient descent, trying to optimize, minimize the error on a large training set. There are at least, I think, 3 types of questions that you can ask. One is really approximation theory, is when and why are deep networks better than shallow networks? What is the representational power? The second one is about the optimization. When you are using stochastic gradient descent, even in networks relatively simple like the ones used to solve CIFAR, which is a mini version of ImageNet, you have like 60,000 data points, images 32 by 32 pixels, and you have up to 1 million parameters. So it's a huge optimization problem, and the fact that you can actually minimize the error on this is quite impressive, that it converges. The third one is that it's really a machine learning theory problem, is the fact that the networks that you find by the optimization process are largely over-parameterized. And so you'd expect them to overfit and not to generalize. But instead, they seem to do pretty well on new examples. So those are 3 key problems, and let me go through all of them, especially the first one. So the first one is why and when, especially when, are deep networks better than shallow networks? First of all, the second one is about, as I said, the landscape of the empirical risk, and the third is about the generalization problem. Okay, so let me give you some background. Typical shallow network, one-layer networks are networks like support vector machines, radial basis functions, regularization networks, in which you are minimize an empirical loss. It's a functional comprising an empirical loss part, V could be the square loss, and then a regularization term, like the norm in a reproducing Karen-Hilbert space. And the solution of these things, independently of V, more or less, is always in a linear combination of kernels evaluated at the examples. And you have as many parameters as data. That's important in this type of networks. And these networks can be essentially written as, this equation can be written as a network with, as I said, as many parameters, the C, the weights, as you have data points. All right, now, from the point of view of approximation theory, it is known since the 80s, at least, that if you have a generic function of n variables, say in this case 8 variables, you can approximate it arbitrarily well in the sup norm on a compact domain by a one-layer network, where the nonlinearity can be essentially anything but not a polynomial. Okay, in particular, it can be the linear rectifier that we described before. So each unit has that form. So it was partly because of this universality property that people did not explore very much the multi-layer option because you don't have any advantage from the point of view of approximation, apparently. There is, however, a problem, and this is well known, is that if you want to approximate, to learn, to represent a function of an d variable, say in this case 8, you have this, what Bellman called the curse of dimensionality. You need, in general, an exponential number of parameters, units in our case. So if you want to, for instance, to approximate a function within epsilon, say epsilon is 10% in the sup norm over a certain range, you need a number of units that is epsilon to the 1 over epsilon to the d. So for instance, if epsilon is 10%, 1 over epsilon is 10. If d is 8, here we have 10 to the 8. But if d is 1,000, like you have in CIFAR, you have 10 to the 1,000, which is a very large number. Okay, so that's a big obstacle. How do you avoid it? Well, classically, what people have done in the past is assumptions on the target function, the function you have to approximate, in terms of smoothness. Because if the function is smooth, then the exponent that appears, epsilon 2, is the dimensionality divided by the smoothness, like the number of derivatives. But another way is to consider functions of this type that we call hierarchically local compositional functions. So it's a specific set of multidimensional functions, in this case 8 variables, but it can be in which it's a function of functions, but all the constituent functions have dimensionality 2. More in general, a small dimensionality. For instance, in the case of, say, CIFAR, or all the cases in which you use ResNet, the kernel there is about 3 by 3, so that would be the dimensionality of the constituent functions. Now, this is an assumption not on the network, but on the target function that you want to approximate to learn with the networks. So assume the target function has a structure like this, then we can prove that you don't have anymore the curse of dimensionality. So in other words, the number of units that you need, if you use a deep networks with an architecture similar to the architecture of the function, does not need to be the same, then instead of the exponential dependence on the dimensionality, you have a linear dependence. And the key part here, that the miracle of avoiding the curse of dimensionality is not because of weight sharing. So convolutional networks are a special case of this structure. But the key is not the weight sharing, is the locality of the constituent functions. Okay, so for instance, I don't have, okay, this one. Yeah, so weight sharing would mean that each of these constituent functions at each level are the same function. The weights are the same. So all these are the same, and then these two are the same. And then, so this would be weight sharing. But the magic in avoiding the curse of dimensionality is that you have function at each node that depends only on 2 variables, that look only at a small part of an image if the inputs are an image. The proof is actually pretty simple because it essentially says that you're approximating within epsilon at each stage, and the error you're making propagates in a good way. It's not amplified as you go up the architecture. So, and by the way, this is really related to a very, very basic thing. Suppose, what is the simplest representation of a function? It's a table, right? So In one dimension, suppose you have one variable, you have 10 bins, so you have 10 entry in the table. Two dimension, you start to have 10 to the 2, 100 entry. If you have 8 dimension, it's 10 to the 8. Okay, that's the curse of dimensionality. But if you have this compositional function, instead of having one d-dimensional table, you have d, for instance, two-dimensional table, which is, of course, much less. Yes?
Does it mean that it doesn't consider long-term dependency?
Sorry?
Does it mean that it cannot consider long-term dependency?
Yeah, although it's interesting because you don't have long-term dependency right here at this level, but at the end you will have them. So yes, and of course you can approximate any function you want arbitrarily well, even if it's not compositional, by superposition of compositional function. Just that at that point you lose the exponential advantage. Okay, and as another generic remark is that what I described is a special case of compositionality, this hierarchically local. In general, compositionality just means function of functions, and that's a very generic statement. The theory of a recursive function in computer science tells you that every function, computable function, can be essentially constructed from the composition of a few elementary functions. So every function is really compositional. In particular, I can write as an iterative scheme, this would be just to map inputs into the same number of dimensionality, but I can iterate, this would be iteration f of f of f. And so I can write a finite state machine in this way, and if I let T be arbitrarily big, this is a Turing machine. So that's a very basic statement I'm making about compositional computations. So to summarize, we have up here is the graph of the functions. This is the target, what I want to learn, what I want to approximate. And the networks are also functions, but they are the functions I'm using, parameterized function, to approximate these functions. In general, if I only know it's a generic function, I cannot do better than what shallow networks do, even with deep networks. But if the function has a structure like this or other particular structures, then deep networks can avoid the curse of dimensionality and be much better. Let me skip this. In particular, there are a number of cases. One is when you have this low dimensionality of the constituent function or high smoothness of some of the components. And then also sharing of tasks in learning. So if you have, you can think of a composition, for instance, in a deep networks, the first layers to be used for a variety of tasks, for instance, different classes, and the final layer or so is common, then you save quite a bit on sample complexity. So there are a number of reasons why compositionality is interesting. And just to mention, we did a number of experiments just verifying these results. Here is one on CIFAR, in which we have a shallow network. This is training error, this is testing error, and these are epochs in the SGD algorithm. And this one, the best performing is the convolutional with shared weight, but giving up the shared weight, just keeping locality also works pretty well. And by the way, as an historical comment, this is which is related to this conjecture about compositionality. I call it conjecture, but that Joshua Benjo had several years ago. is these results about avoiding the curse of dimensionality and so on are very closely related to all the results on Boolean function, on logical circuits, in which that say that certain functions, like the parity functions, can be represented much more efficiently by a deep circuits rather than the shallow one. Okay, so it's an interesting question, open question, is why compositional functions are probably a set of measure zero in the space of all possible functions. So why are they so interesting? Why they seem to come up in vision, in speech, in language, in text? Well, first of all, let's notice that speech and text are man-made, and they are compositional almost obviously. Like text is made up of letters, of words, of sentences, or pages, chapters, and books, and so on. And speech is similar, but vision is a bit different. So why, for instance, vision should be compositional? A colleague of mine, Max Tegmark, says this is because of physics. It's because the Hamiltonians that are generating the universe and things in the universe are pretty local. And so this is kind of a generative process that implies that the inference process is also local. This may be. I'm more of the idea that it may be a consequence of neuroscience. So in other words, suppose that the brain evolution finds easier to make local connections. For instance, in our visual system, we know that there are photoreceptors, and then there are ganglion cells, and the ganglion cells in the retina only look at a small number of photoreceptors, and so on. And local connectivity is much easier to wire up during development. So suppose this happens, then our brain, our visual system will be wired up to approximate well compositional tasks. And so those are the things we can solve and the question we can ask. And so that's why those are the interesting ones we find. That's kind of upside down. This is just to show that one of the main topics of Perceptron was really looking at locality of computations. And for instance, the cover here show a spiral, and the task is to decide whether it's which one is connected or not. And it's something that is not a local computation, and we find very difficult to do. Okay. So, second, the optimization theory part. This is relatively some observations. One is that suppose I'm writing the exact solution. So that's looking for the function, which is the network that exactly fits the data. Okay, so in the case of CIFAR, for instance, you have 60,000 equations with a few 100,000 parameters. Now, the parameters come in a form like this. It's a linear combination of some of the variables and then the rectified version. So this is each one of the units in a network. Suppose that I make a univariate polynomial approximation of each of these terms. So this would be a polynomial in one variable, which is this linear composition of x1 and x2. Could be a polynomial of order 3 or 4 or 6. I forgot we used one. But you can think of it as a polynomial approximation of the actual network, which I can use a degree which is high enough that the approximation is as good as I want. And then if I do this, then I have a large set of polynomial equations, and I can apply some results about the solution these systems have. More direct, if you don't believe in the approximation approach, you can replace in the network, actually replace, the rectifier with a polynomial approximation, which we have done, and you find that it behaves essentially in the same way as the one with the rectifier. So that's training error, test error for the actual RLU network, and this is the polynomial one. So at this point, you can use Bézout theorem that tells you how many solutions a set of polynomial equations give you. Actually, it tells you an upper bound. But the upper bound that you get is very high. It's like more than there are atoms in the universe. So this means you have a lot of solutions of these equations. If the equations are consistent, which means if your networks can actually approximate or actually represent the function that originates the data. Because there are more parameters than data, the theorem tells you that, like in the case of linear equations, the solutions are degenerate in general. So the solution that give you zero error are degenerate because you have 60,000 of them, but many more parameters. Whereas the solution for the local minima, the zero of the gradient, are as many as the weights, because you have to put all the gradients to zero. So in generic term, you have that the zero solution are degenerate, so there are actually varieties of infinite solutions. And the critical points, the local minima, are not degenerate, generically. Okay. So this brings up to the next puzzle, which is that, as I mentioned, despite the fact that the zero minimizers are degenerate, and you have more parameters than equations, you still, in general, you seem to do pretty well in terms of a prediction of expected error. And the reason is a few properties that I don't know if somebody knows. I'd love to hear, but I don't think this has been remarked before. Some interesting properties of stochastic gradient descent. It seems that stochastic gradient descent is minimizing, but subject to the constraints of finding flat minima. And this means degenerate minima. So that will mean that we'll preferentially find exactly the zero minimizer instead of the local minima. And furthermore, as we'll see later, this large minima correspond to solution that generalize is not the right word, that have good expected error. So, first of all, let me start with what is in physics is called a Langevin equation, which is essentially the motion of a particle under Brownian noise. So this is the derivative of the Brownian motion in a potential field. Actually, I have a notation problem. This V should be U, so a potential U is the same. So this is a stochastic differential equation. This is the full gradient. And the asymptotic, the probability distribution of F, so asymptotic in the sense for time going to infinity, is the Boltzmann distribution. I have another typos here. There should be no equal. It's just a normalization constant, but this is e to the minus the u, which would be, in our case, the loss function. Okay, so you can see immediately that the loss function will depend of, in our case, the parameters that matter are the weights. So there will be 300,000 or so weights. And so if you have, suppose you have two minima, that's your u, two minima, which one is a bit larger than the other. This is actually twice, but 1.001 will have exactly the same effect. One is larger. Then if you look what happens in one dimensions, this is the Boltzmann distribution, what you find, stochastic gradient descent. This is in 2 dimensions, in 3, in 4, 5. In other words, as the dimensionality increases, the smaller minimum disappears in terms of your solution, although they have the same depth. So stochastic gradient, well, in this case, the Langevin equation minimizes, but among the minimizer concentrates, because of the high dimensionality, on the larger minima, because all the volume and the probability mass is there. So this also means that if you have a degenerate minimum and another one which is not degenerate, it will preferentially find the degenerate minimum. And this becomes, again, this is in 1, 2, and 5 dimensions. So, and we have 300,000. So we have a very large concentration effect due to the large dimensionality. Okay, this was for the Langevin equation, but the stochastic gradient descent, which is taking the gradient of one point at a time or a small mini batch, can be written as a Langevin equation in which you have a pseudo noise that is actually the difference between the full gradient and the mini batch gradient. It is a particular type of noise, but has basically Gaussian projection because of the central limit theorem on the mini batch. So for the right size of mini batch, it's very similar. And empirical, we find behaves in the same way as the Langevin equation. So this means that stochastic gradient descent will find large flat minima. Large minima usually have a flatter region than the smaller ones, and it's possible to connect flatness and volume to the margin in the classification case, to the classical version of the functional or geometric margin between classification boundaries of, say, 2 classes. So this means that stochastic gradient descent will minimize with the constraint of finding the largest, the flattest minima corresponding to the largest minima. And large margin implies good generalization, where of course good generalization depends on the distribution of data. And so this, I think, explains some of the puzzles, recent puzzles. This was, it's what happens in CIFAR when you go with the number of examples above the number of parameters. So this is a case in which we have 10,000 parameters. We have, when the number of example is smaller than the number of parameters, we have 0 training error, and the test error is going down, And then it continues to go down as you increase the number of examples beyond the parameters. This is usually something people don't do, right? And here is what happens in the case. This was a student of mine, and Sami too. This was and Ben Recht, and I forget the other authors, but showing that if you have random labels in CIFAR, then of course the test error is random, it's chance, so 0.9 because there are 10 classes. And what you can see is that you have training, your model can still fit the data, so as long as the number of examples is smaller than the number of parameters. But then, so this was the puzzle, that you can fit the data, and this is the same network that does pretty well with normal labels. But then when you increase the number of example, your training error starts to appear and increases, and probably asymptotically will get to the test error. So this would mean generalization or a gap. And this one I find even more interesting. This is now fixed number of data, 50,000, and then we increase the number of parameters in the same architecture. And what you find is that the training error goes to zero, essentially, basically at training data number equal number parameters. And then you increase the number of parameters, and your testing, your test error remains the same. You don't have overfitting. That's the kind of surprising part. But in terms of the theory, I said, it's just that you get, at this point, you have a large margin solution, and if you increase the number of parameters, the over-parameterization is basically not seen by stochastic gradient descent. Stochastic gradient descent, so degenerate direction are invisible to stochastic gradient descent because the gradient will be zero. It's exactly the same argument that one uses to prove that stochastic gradient descent in the linear case finding the minimum norm solution. So I think we can explain, not quantitatively, but qualitatively, all of these puzzles. And so let me conclude. I think it's important to understand that there is much more work to be done along the lines or in other direction along the lines I described. The hope is that if we understand better how they work, then we can understand better how they fail, which is important for practical application, and even more importantly, how to improve them. And one of the improvements, of course, would be to try to reduce the number of labeled examples, because that's still one of the problems today. I think one can look at the story of computer science and think we have at least 3 ages. One is the age of programmers. In the age of programmers, you have to pay very smart people quite a lot of money to make some system behave in an intelligent way. We are now in the age of labelers, in which you pay a lot of people not much money in order to label data. And both of them, especially this one is n going to infinity, number of labeled data going to infinity. But of course, children don't have big data. We really would like to to be able to show one car and one plane to a child, like we do for a child, and then they're able immediately to generalize very well. So our ideal is n going to 1, and to have computers that learn like children from experience. Thank you.
I have a question. So, okay. I have a question. I will raise my voice.
Раз, два.
Раз, раз.
Okay. So now I can use two, right? All right. So that's very convenient. Okay. Anyway, so we basically I find very illuminating what you found about the stochastic gradient descent. So in a way, I would like to ask a provocative question.
Yeah.
So if you I mean, in a way, a stochastic gradient descent is an algorithm that works with a lot of noise. That, in a sense, noise is a program. It's almost, it's also includes some regularization because you've actually shown that, right? So, in a way, you're using the optimization to also imply some regularization. You could also turn things around and say, why not define the proper loss function and use a proper optimization, and then go to the right optimum. And so I wonder whether you've also looked at like a Newton or something which would not have this noise included. What would happen there?
Yeah, no, it's a good question. Of course, we have not yet explored, how to improve. That's part of the program. As I said, we're trying to understand first what's going on and then possibly to improve it. So I really don't know whether it's possible or whether SGD is the best we can do right now. I don't know. It seems pretty good. I find almost magical the fact that it finds the degenerate solution, and those under those conditions are also the ones that do best in terms of expected error for classification anyway. It does not mean it's the best one. So yes, that's.
I mean, I feel it's like you're shifting the regularization. It's like you shift the joker from one side to the field to the next, and it's not clear which way to.
Right. Well, first of all, it's not clear, and I'm not sure. We did answer completely this question. It's not completely clear the implicit regularization, what it is exactly, and how to characterize it that you have in SGD. Because if you write it, there is no regularization term, right? So it's already interesting to find that essentially the noise has this effect, and I've tried to explore. There is a connection. I have some results on a connection with so-called robust optimization. That it's optimization subject to. So you're looking for a minimum that is the most tolerant to perturbations in parameters or inputs. And so there is a connection there, but it's not perfect, especially I think it's rigorous in the linear case. I can make it rigorous in the linear case, but not, so this would mean one layer networks, but not in the multi-layer ones. So there is more work to be done there. In that case, the connection regularization is very clear. You have a quadratic or other norm regularization terms coming out. But otherwise, it's kind of implicit in this concentration phenomenon. So what I can say that SGD finds the minimum among the minimas with the same minima, it selects with very high probability the one which has the largest volume.
So, does it work? Yes.
Yes.
About this, the idea that flat minima are good. Maybe you know about our recent paper showing that you can easily change a solution that is a flat minimum to another one that is not at all, but it's the same functional. So how do you get?
So yes, well, your result does not say that flat minima don't generalize, right?
No, that's true.
Right.
But it says that it's not because it's flat that it's good.
But I don't think it works for isotropically flat minima. So if they are flat in all weights, then you cannot.
It basically shows that if you take a flat minimum solution, you can make a very simple transformation that doesn't change anything in the functional.
Yeah, but suppose it's flat in all the weights.
Yeah.
You know, you can. Then it does not work. The renormalization you do.
I see. So you're saying some flat minima cannot be transformed into some solution that has
isotropically flat.
I see. Okay.
You cannot correct. And we find empirically that we have isotropically flat minima.
Yeah, so I found actually your first part very interesting. My question is as follows. So the universal approximation theorem says that basically you can approximate every continuous function on a complex set arbitrarily well, but it doesn't say much about the complexity of those networks in terms of maybe the number of neurons or in terms of the sparse connectivity. So my question would be, in your setting for your specific functions you consider, the networks you use for approximation, are they in some sense optimal in a certain sense? Are these optimally sparsely connected, or do they have, let's say, a minimal number of neurons? Are you interested in that question, or do you have any thoughts on that?
So let's see. We say, that for a generic continuous function of a certain smoothness, so for instance, our setting is in a Sobolev space in which you have a dimensionality D and, say, S derivatives. And we can say that generic function will have, in terms of approximation by a deep network, will require a number of parameters that is not exponential in the dimensionality. It will be D over S. So we can say this, and we then have a number of examples of specific functions, and these other people like Telgarsky, which cannot be approximated by shallow networks. So I think in terms of complexity, we give this rate of approximations for. I don't know what exactly you can do more in that direction.
You show that stochastic gradient descent is mostly insensitive to overparameterization. And the example that you presented this on was 50,000 labeled samples. I would like to suggest that if you would use much less, maybe not even 100, maybe 10 samples or 5 samples, then this would no longer be insensitive to overparameterization, and the exact parameterization is going to be much more important. So
you are saying instead of 60,000 data points to have a much smaller number?
If you would be in this case, where you're trying to learn with very few training samples, then the structure that you enforce on the network is much more important.
Well, the structure of the network, let's see. Oops, I think you are. So you are interested in this range?
So
This will be training examples.
So the slide with the fixed number of training examples, but the different number of parameters. I think it's one before the last slide.
This one?
This one, yes. So if you would run this experiment again, but instead of 50,000 different training samples, you would have 10 samples. Or 50, or 5.
Yeah.
Or 1, yes. Or 0, because I'm actually thinking about unsupervised learning.
You mentioned the structure. So what exactly do you mean by the structure?
So my hypothesis is that when you apply unsupervised learning, then the structure of the network, which relates also to the first topic, the type of compositionality that you apply, is where you actually give the hint how to treat the data.
Say it again. Sorry.
So what I'm thinking is that in unsupervised learning, and in the last year, we had excellent results in unsupervised learning coming from all sorts of groups, basically things that we didn't think were even possible. For example, all the cycle gun type of work. I think much of it is because that the structure of the network dictates the solution. And over there, you cannot assume that overparameterization is going to give you the same outcome.
Could be. I'm not sure I understand completely, but of course the structure of the network is important also in the supervised case. In this case, the compositionality structure is important, and you need to have the network representing. Ideally, it has to be able to implement a function which is which includes the target function, right? The function that actually produces the data, the conditional probability of y given x.
According to this curve, I assume that if the training data size was smaller, the green curve would be on the left, and the yellowish curves would just be higher.
Say it again. It will be on the left.
Yeah. I'm extrapolating. If the green line was on the left of what it is, the extreme being on the axis, then the test error would be very high. That's I guess.
My question is more whether the orange line would remain horizontal or whether it would actually fall.
Yeah.
Sorry.
What do you think? What's the answer?
I think that with very few training samples, you wouldn't see this phenomena of insensitive to overparameterization. So if you use too many parameters and you're in the regime of n equal 1 or unsupervised learning, then you would see that it's very important to use exactly the number of parameters that you need in order to model the problem.
Yeah, I agree. I think I agree because it's you will not be able to implement the approximating function that is powerful enough, right? If you have too few parameters. Another way to say.
So you need more regularization, and it can be in many forms, including the structure.
Much more regularization, but so this is surprising because you don't need regularization and you add parameters and you still get this plateau of performance. And I'm saying that in the case where you have very small n, you need more or less exactly the minimal number that you need to actually express the function, but not much more than that.
Yeah, I agree. Yes. Mm-hmm. It's interesting that I guess this was the point in your paper with G1. the classical theory has been emphasizing generalization, which technically is the convergence for n going to infinity of the training error with the generalization error, the test error. But here, in this regime, you don't have generalization, right? You know, if you have, say, suppose you have more parameters than data, and you make both go into infinity, I bet that you never have generalization. You never converge. And this is actually quite well known because one nearest neighbor, which is the simplest possible learning algorithm, has exactly this. You know, it performs pretty well. I mean, there is this bound that it cannot be worse than twice the Bayes error, but you never have generalization.
So I'm quite interested in the last part, implicit supervised learning. So far already we have a lot of research. I don't know, either like deep architecture is the key, or semi-supervised or unsupervised learning is the key, or transfer learning or regularization. So what do you think would be the key challenge for this implicit supervised learning? Do we need a completely new concept?
Well, we have to try and we'll find out. Yeah, I don't know. I don't think we need completely new concepts, but I think that there are a lot of tools. But there is certainly a lot of work to be done still. Very interesting results to be found. In particular, I find it interesting that when I was studying physics many years ago, we were told in order to fit parameters, you should have, at least twice the number of data as the number of parameters, or 10 times is better. Then we got in a stage with kernel machines in which you have as many parameters as data exactly. And now we are in the era in which having more parameters than data is a must, right? And so it's very interesting. I think we can understand all of this, but it opens up new possibilities. And I'm not sure we really understand yet how to use it optimally. Back to your question. Yeah. I hope not, so then we can improve.
Yeah, so maybe if I can ask another question concerning the first part. There's also this work by Shashua and his PhD student Cohen.
Yeah.
They use a tensor structure in some sense on their model. Can you say a bit how this relates to your work? I mean, is it included in your work? Or?
Yeah, that's a good question. I think that this theorem we have on compositional functions is actually the foundation for the tensor work. So they use the hierarchical Tucker decomposition of tensor that is actually very similar in terms of the organization to this hierarchical compositionality that we have. And in the tensor literature, I never found theorems, results that say that characterize the class of functions for which the hierarchical Tucker decomposition works. I think our theorem just says that.
Thank you.
So in the first part, you mentioned that having multiple tasks to solve improve the performance of the network.
Yeah.
Do you have any quantitative result on this?
Well, there are some results, actually not by us, but by Andreas Maurer. I can give you the reference. There are some bounds on the sample complexity that depend on having, in our case, part of the network be used for a different number of tasks, and then another part that is specific for each task. So it's pretty generic. Yeah.
Okay, thank you.
So I was wondering, in which way does the size of the mini batch affect the efficiency of stochastic gradient descent? Because the noise is pretty important, right?
Yeah.
And you said that the noise behaves similar to the Brownian noise.
Yeah.
And that's why it probably generalizes so well or finds the flat minima. So maybe that also relates to the question before. If you have lower training size, then you don't have so much noise. And I was wondering, until like how, if I increase the size, like how does it affect the efficiency? Does it suddenly behave good? Like, is it suddenly efficient, or is it gradually? It's always taking one sample, highest probability to find the flat minima, or I don't know.
So I cannot tell you, let's see, we have not looked yet at this. This is very recent work, it's partly unpublished, right? We have not looked exactly at this question, but I can tell you qualitatively what happens. If you have the mini batch, which is very large, then you are doing gradient descent. And then you may have the risk of finding, local, in principle, local minima, or get stuck in local minima. If it's too small, then let's say if it's medium size or not too big, not too small, then within the mini batch you have the central limit theorem working, and so the noise we see, the pseudo noise, is really Gaussian. I don't know how important that is for the kind of behavior of the Langevin type equation, but it's not. You don't need the mini batch to be too large in order for the central limit theorem to give you essentially a Gaussian type noise. So that's it should not be too small, like just a single point. Well, then you lose the Gaussian property, and I don't know whether that's but then it's not similar to the Langevin equation. So I don't get the Boltzmann distribution. It probably does not matter too much. But
I haven't seen any empirical results showing that smaller mini batches are bad in any way, except that they are slower for.
I think there are. I think you're right. There are some empirical results saying that if it's too large, it's bad. Right? Yeah. Yeah. I've not seen.
The other side, I haven't seen.
Yeah. No, that's my guess too. It's just that if you want to have a good approximation of the Langevin equation, then Gaussianity is important. But my guess is that probably everything will work even if the pseudo noise is not Gaussian.
Yes, I mean, there is also a price when you have like more parameters, right? Because your model becomes less interpretable. It takes longer to compute, or it takes more space to store. So do you think in future our models will proceed in this direction, that we will have larger and larger models because of the properties which you showed? Or do you think there is also like this trade-off, and which is kind of also important for practice?
Yeah, well, I hope that developing a theory will help understanding how these things work. Understanding does not necessarily mean understanding which each unit is doing. That may be too much, maybe not the important thing, but understanding the properties and which kind of failure you can expect and so on. In terms of having a lot of parameters may be a problem for hardware implementations. Compression of networks people are now starting to design special purpose hardware, so reducing the number of parameters is important for that. But otherwise, having more parameters in training probably makes it easier to do the minimization at training time, finding finding zero errors solutions is much easier if you have over-parameterized, especially because of these properties of stochastic gradient descent that seems to prefer degenerate minima. So I don't know, it's a trade-off. It's an interesting one.